Pues regresamos.
Hello, can I share my screen?
Yes, I please, one moment, please.
Oh, okay.
Bill, ¿su micrófono está apagado? Yes.
Bill Pesh, your microphone is off.
Yes. Yes, thank you. Thank you very much. It reminds me that I wanted to mention also to some of the presenters, some of the panelists, that they may not be aware that they're transmitting video, that there is a possibility of turning off the video using a control button at the bottom left of the screen, or also by clicking the Alt plus the V key. So it just seems that some people are streaming video, but they're not really aware. We are beginning our second session today, and our keynote speaker is Gowen Meng. I hope I don't mispronounce your name too badly.
No problem. Correct.
So I would just like to read this short biography. Gowen Meng graduated from the Department of Modern Physics of the Chinese University of Science and Technology in 1986, and then studied theoretical physics at Brown University in the United States. As a CUSPEA student, he received his PhD degree in mathematics in 1993 and has been teaching in the Department of Mathematics at the Hong Kong University of Science and Technology since then. He was awarded tenure at the end of 1998 for his independent discovery of the Meng-Tubbs formula, linking the Schwielberg-Witten invariance and the Alexander polynomial invariance in low-dimensional topology. A member of the Institute for Advanced Study for the academic year 2010-2011. His research work has revealed the rich mathematics behind the Kepler problem, ranging from symplectic geometry to harmonic analysis. And thank you very much for participating in our conference, and I'd like to invite you to proceed.
Okay. Thank you for the introduction. It's a great honor for me to be given a chance to give a talk in this international conference in memory of Professor Zbigniew Ozowicz. I met him in year 2012 in the international conference in mathematical physics. But back then he shared some of his thoughts on relativity. And to me, those thoughts are strikingly new. And then in the year 2016, he and Hilda visited Hong Kong briefly. And during the visit, he impressed me with a beautiful drawing for mass identity. So that identity is a camel and its mirror are equal. There's a photo here. I believe this photo was taken by Hilda as the magic square of our math department. So today I'm wearing exactly the same T-shirt as the one here, okay? So the background photo is Riemann, and this is a great applied mathematician, Shannon. Okay, let me formally start my presentation. So there's a link between two things. One is a Kepler problem, the other is a
Excuse me?
Jordan. Hello?
I think, are you intending to share your screen?
Oh.
We don't see your screen.
Oh, sorry, I forgot. Okay.
So perhaps you could show your t-shirt again.
Oh, yeah.
Thank you.
Okay. Can you see, this is a t-shirt I'm wearing today, and this is a t-shirt I wear five years ago. Yeah, exactly the same one. Okay, this is a photo taken by Hilda.
Thank you. We see that very well. So please continue.
Oh, okay. Thank you. Okay. What is the Kepler problem? Well, there's a classical mechanical model for the simplest solar system. So in the solar system, there's only one planet. Okay. It was introduced by Newton around the year 1678. And the solution of this model give us a satisfactory explanation of Kepler's law of planetary motion. And when we quantize, we get a quantum mechanical model. People usually call it Coulomb model. Okay, that is a physical model for the simplest atom, namely the hydrogen atom. So that quantum model was introduced around the year 1925, and its a solution gives us a satisfactory explanation for the periodic table, and also the Balmer's formula for the spectral line of hydrogen gas. And this model combines beauty, simplicity, and truth into a single entity. Okay, let me introduce the Hamiltonian and its symmetry. First of all, there's a phase space for this Kepler problem. So that is the total cotangent space of the Euclidean space with a point removed. So this means the Euclidean 3D space with 1 point removed, then the total cotangent space. So that is a phase space for this Kepler problem. And then we have the standard coordinates. So this is a position coordinate, this is a momentum coordinate. So in terms of standard coordinates, the Poisson structure on this phase space can be described by this basic Poisson bracket relations. And the Hamiltonian is like this. So I take the mass equal to 1, okay, for simplicity, because we're doing mathematics. And this is a so-called angular momentum, and this is a length vector. Okay, and then in terms of Poisson bracket, one can check that the Poisson bracket of the angular momentum with the Hamiltonian would be 0. This is really a restatement of the fact that angular momentum is a constant of motion. And this length vector is also a constant motion. So that means it's a Poisson bracket with Hamiltonian should be 0. Actually, direct computation shows that this is true. Then I introduced something called length algebra. And so suppose Li is the ith component of the angular momentum vector, and the Ai is the ith component of the length vector A. And then these two identities says angular momentum is a constant motion, length vector is a constant motion. And this is automatically true because this is the angular momentum. They generate the Lie algebra little SO3. So it goes satisfies this relationship. And this epsilon tensor is this equal to 1 if ijk is the even permutation of 1, 2, 3. It's equal to -1 if it's the odd permutation 1, 2, 3. Otherwise, it will be 0. Okay, and this is also obvious because this is A after all is a vector and SO3 rotation. So this is automatic true. So all these are automatic true. And finally, this one, we need a little bit of computation. So we get this answer. So the algebra, say associative algebra with a generator L and A and also H satisfies this relation. We call it length algebra. Okay. Now, the next, what is the Jordan algebra? By the way, this Jordan is a physicist. He is one of the founder in so-called new quantum mechanics. So he formulated algebra. Nowadays, we call it Euclidean or Jordan algebra. In the old days, people called it formally real. Okay, so what is that? We are only interested in finite dimensional. First of all, it's a real algebra, and it's a commutative. So it's a product like AB equal to BA. Okay, it has a unit. So there's an element called E times A equal to A times E equal to A for NA, such that we have these two identities satisfied. So this I call the weakly associative. So normally for associativity, we have three elements, A, B, C. But now the C is just A squared. Okay. And then there's a second condition, people call the formally real, because if the real number satisfies this condition, A squared plus B squared or 0, then we must have the real number A and B equal to 0. Okay, but after all, A, B are not real numbers, so we say this is a formally real condition. It turns out this condition is equivalent to this 2' condition, namely there is an inner product. So I'm using physics notation, Dirac's notation, on this real vector space V. So this is the inner product. And this inner product, this unit element E has length squared equal to 1. And also there's a multiplication by A. So X, this is A times X, okay, is a self-adjoint with respect to this inner product. It turns out that they imply each other. So because of that, so this is the inner product is the Euclidean structure. So nowadays, people prefer to call the Euclidean Jordan algebra. Okay. Now, this has a nice classification. So this Euclidean Jordan algebra are semi-simple. That means it's a direct sum of simple ones, okay? Simple ideas. Okay, the simple one consists of 4 infinite series and 1 exceptional. So this reminds people the classification of Lie algebra. Okay, so the first one is the set of real numbers. This one is even an associative algebra. Okay, all other are weakly associative. So this is even associative. Okay, and let me explain this notation. So this HNR, this means the collection of n by n real symmetric matrix. Okay, then what would be the, well, this is the real vector space. Then what is the Jordan multiplication? Well, it's the symmetrized matrix product. So this is A times B plus B times A, but I do not divide it by 2. Okay, so this is the definition of this. So this is the dot means matrix multiplication. Okay, and this one is a similar. This is a set of n by n complex matrix, but Hermitian, complex Hermitian matrix. So this is a quaternion Hermitian. This is a 3 by 3, the collection of 3 by 3 matrix with octonian number as its entry, but it's an octonian Hermitian. Okay, so when you take the complex conjugate and also the transpose, it's equal to self. So it's like a dagger by definition means A transpose and then complex conjugation in this case. In this case, it would be quaternion conjugation. In this case, it would be octonion conjugation. This should be equal to self. Okay. And how about this gamma n? This is called a Dirac type. So this is one is associated with Clifford algebra. Okay, I have this, well, as a real vector space, is this one-dimensional model vector space direct sum with R to the n. And then the Jordan multiplication is like this. So A, so alpha, and U, that's an element here, then times another one called beta and V. And this should be equal to alpha beta plus U dot V, and then alpha V plus beta U. This is the Jordan multiplication for this algebra. Okay, this is called the Dirac type. So this one is exceptional. It has to do with this so-called octonions. And actually, one can compare Jordan algebra with Lie algebra. Say if we are interested in real Lie algebra, then corresponding things will be called real Jordan algebra. And inside there's a big collection of real Lie algebra. We have a small collection called compact real Lie algebra. That means there is something called Killing form should be negative definite. And here there's something similar. You can define something similar to the Killing form. And that thing should be Euclidean, well, should be the inner product. It should be an inner product. So that's why this side is a Euclidean Jordan algebra. So Euclidean Jordan algebra corresponds to compact real Lie algebra. Okay. Oops. They're not moving. Oh, okay. Oh, so this is the modification, Jordan modification for gamma n. So there's this particular one called gamma 3. Okay. In this case, is isomorphic to H2 of C. In both cases, 4-dimensional. And in the Lie algebra, we have something similar, low dimension. The different class, we have the degeneracy. Okay, here similar. Okay, so this means 2x2 complex Hermitian matrix, and the symmetrized matrix multiplication become a Jordan algebra, and that Jordan algebra is isomorphic to gamma 3. It turns out this is more refined than the 4D Lorentz space, because this, I say this 4-dimensional real space, and then from this Jordan structure, you can derive a Lorentz structure. So that's why this guy is a refined version of this Lorentz space in 4 dimension. So because the Lorentz dot product can be derived from the Jordan algebra structure. Okay, and then for this Jordan algebra, for this Jordan algebra gamma 3, we have the following nested sequence of real Lie algebra. So first of all, this one. This is the infinitesimal symmetry algebra of gamma 3. Okay, so called derivation algebra of gamma 3. And this one is called the restricted structure algebra gamma 3. And this one is called conformal algebra of gamma 3. Okay, but of course, this is well known to theoretical physics because this corresponds to rotations, this is Lorentz group, and this is a conformal group. But then this has a generalization in general. So there's a derivation algebra of the Jordan algebra. This is a restricted Jordan algebra of V, and this is a conformal algebra. So in the special case V equal to gamma 3, this sequence will become that sequence. So this is Lie algebra derivation, okay. And all this also has a geometric meaning, but I don't have time to go to it. Okay, now so-called the structural algebra. So purely on algebra level, I want to tell you what that is. Okay, so remember we have the multiplication by this element A. So this is the endomorphism on V. So it's a linear map from V to V. Okay, so in other words, this is an element in the endomorphism algebra of V, but you can view this as a Lie algebra. Okay, and then we introduce this element SAB. So this means LA composed with LB minus LB minus LA. This is a bracket. Then plus L multiplication by A times B. So this is also an element here. So SAB is also here. But then what is the structural algebra of V? By definition, is the smallest Lie subalgebra of the endomorphism algebra, which contains this SAB. In other words, this is the completion, Lie algebra completion of this inside this Lie algebra. Okay. So it turns out this is also the span of this. Okay, because we can check that when we do the computation computation, and this is closed. Okay, and then we have this called the Jordan triple product. So by definition, it's SAB applied to C. Okay, and you can see that this C and D, they behave differently under the transformation of SAB. We should view this SAB bracket with SAB as the infinitesimal version of the group action. Okay, so C transform like a vector. This D will transform like a covector. So remember on V, we have the inner product. Okay, first of all, SAB is endomorphism on V. Then on the dual space, we have this. But because on V, we have the inner product, because it's called the Euclidean Jordan algebra. So we have an identification of this with V. So this with V. So this action, infinitesimal action, will become this infinitesimal action. So you can check the. So C behave like a vector index, so-called contravariant index. D like a covariant index. But we make identification with D should be up index, but because we use the inner product, we lower it. Okay. Anyways, so this algebra is called a structural algebra. Then we have something called the Tkk algebra, which is really the conformal algebra. So independently discovered by these three gentlemen. So it's like this. So we have the structural algebra of V, and one can check that this is never simple. If V is simple, but this is never simple. But then we can extend this. So we add one copy of V, but we also add one copy of V star. But V star, of course, can be identified with V because of the inner product. Okay. So element here, the generator here will be SAB. Element here, say little u, but I rewrite as XU. Element here, well, can be, I say alpha, but it's identified with something called V. I write it as YV. Okay. And then the completion of this structure, computation relation is almost obvious. This is the original one because the structural algebra satisfies this commutation relations. And this one is true because Z behave like a vector. And this is true because Z behave like a contravariant, a covector. So that's why we have this. But then there's a grading. So this is the graded degrees here is 0. In physics, this is like the dimension, physical dimension. So the dimension, angular momentum has dimension 0. And here, one is a position, other is a momentum. So one is a -1, other is a +1. So the momentum is a +1. Okay, this is -1. And you want this commutation relationship, preserve this grading. So if you take
Excuse
any
me.
2 here, it will be in degree -2, but there's no degree -2, it has to be 0. Here, if you take any 2 elements here, say yu, yv, you do bracket, should have a degree or physical dimension 2, but we don't have such things, so it should be 0. But if we take 1 here and 1 there.
5 minutes.
Oh, okay. It's running so fast. Okay, so this has a degree 0, but this also has a degree 0. Okay, so then we choose a normalization constant like this. Okay, that will make a certain formula beautiful. Okay, so it turns out this is a simple Lie algebra. It's a real simple algebra. It's called Tkk Algebra in the literature, but we prefer to call it conformal algebra because it's really the generalization of the conformal algebra SO24. Okay. Now, I want to talk about universal Kepler problem. Okay. So first I introduce this Tkk. That means, first of all, there's a conformal algebra. I have the universal enveloping algebra. Okay. But then I want to, I also want to complexify it. But also I want to formally invert YE. You remember E is the identity element in the Jordan algebra. So there's a YE. Okay. I formally invert it. Okay. Then we can introduce this definition. Okay. So first of all, there's a universal angular momentum. So it's given like this. So this is the element in here for each pair of elements in V. And there's a universal Hamiltonian is given by this. So there's a E. So you have XE and also YE. So we can construct this element in this algebra with YE formally inverted. So we have this. And then there's a universal length vector. It's given by this. Okay. So why does this definition make sense? Because we will have I didn't put that page here. It turns out they will satisfy the similar relationship. Like if you do the bracket L with H, you could be equal to 0. And if we do A with H, the bracket, because this is associative algebra, then you can do the bracket. This be equal to 0. And also you can do the angular momentum things. This is something like L. And also you have something like LA is like the A. And then you have the AA things. This is like a -2HL, something like this. So this is justify this definition because they satisfy the generalization of the, this is generalized the length algebra we introduced earlier. All right, so now it become clear how to obtain a many integrable model which shares the Kepler's problem's characteristic feature, such as the existence of a length vector and a hidden symmetry. So the steps are the following. So start with a simple Euclidean Jordan algebra, and then we have the conformal algebra. Suppose this conformal algebra has a concrete realization, then we plug in. So this is abstract elements. Once you have realization, then we get a concrete model, okay, of Kepler type. And then the realization, we have either operator realization or Poisson realization. If we use operator realization, a suitable kind, then we get a quantum generalized Kepler problem. If we use Poisson realization, we get a classical Kepler problem. So there will be many, many problems, even for a single Jordan algebra. So this is similar to things like universal R matrix and my R matrices, okay? Because each quantum group, a representation will give you a concrete R matrix. In spheres are similar. Okay. Now I skip this.
Conclusion.
Yeah. So conclusion, maybe I just say here, well, I skip this. I just want to say the Kepler problem corresponds to so-called the gamma 3. And also the harmonic oscillator correspond to H3R. Just one of the problem. But we know the Kepler problem has an unbounded sector. Harmonic oscillator has an only bounded sector. So I should say there is a Kepler problem with a configuration space equal to, well, something called the Kepler cone of this Jordan algebra. Its bounded sector is isomorphic to isotropic oscillator in the Euclidean 3D space. I should have. I just want to say this Jordan algebra captures the essence, mathematical essence of the Kepler problem, the Jordan algebra, so that we have a general theory, so that we can unify the Kepler problem with the oscillator problem under one roof. Okay, I should finish. So I would like to thank the organizer of this conference for opportunity to present my work here. And to my friend, Zbinisov, we always remember you as a friend, and more importantly, as an original and a critical mind. He gave me this striking impression that he's very original and also very critical. Okay, thank you for your attention.
Thank you. Thank you very much for your presentation.
Yeah, thank you.
We will invite people to ask questions through Q&A or on chat. You can respond that way if possible.
Sure.
So we will continue now with our next speaker. Our next speaker is Ludmila Sabina. Ludmila was born in Moscow. She studied at the Moscow Lomonosov State University and wrote her thesis in the area of algebra under the supervision of Alexander Olshansky. Her doctorate was completed in 1992. She came to Mexico in 1992 and did her postdoctoral work at the UNAM Institute of Mathematics. She is currently a professor at the Autonomous University of the State of Morelos, and she has more than 30 scientific articles. For the last 30 years, she has actively participated in the conferences and organized the annual workshop in algebra and topology. Its central interest of this workshop is non-associative algebra. So thank you. And Ludmila's slide presentation is available now. So please carry on.
Oh, thank you. One moment. Thank you. Yes, my title of my talk, you can see some recent results in the theory of binary algebras and how to change this. Compartir pantalla. ¿Cómo puedo mover mis...
Попробуй мышкой.
How to move my slides? I don't understand here. One.
Maybe if you go out of the complete screen, and then you can move this.
Perdón, Leonila, si quieres, nosotros proyectamos tu presentación y tú las puedes ir comentando.
Ok, entonces
¿Sí?
la siguiente página, por favor.
Sí, por favor. Sí.
Ok, I will.
Pero si dejas de compartir pantalla, por favor, ahorita.
Pero ya se está viendo, ¿no?
¿Y cómo compartir? ¿No,
No,
compartir
no.
pantalla?
Lo único que
No
yo creo
puede.
que lo que tendrías que hacer es que se vea tu imagen nada más en la cámara, ¿no? O sea, abrir tu cámara y nosotros estamos proyectando la presentación.
Ok,
¿Sí?
entonces voy a comentar, sí.
Sí, por favor.
Me gustaría, okay, I will speak in English, I think. First time I met Professor Zbigniew Asievich in Oviedo at the conference on non-associative algebra and its application in 1993. And immediately I was impressed of his extraordinary personality. At the time, Professor Zbigniew Asievich and me, we were two persons from Mexico participating in this conference. After Oviedo conference, there were many conferences, meetings, and discussions. We met many times with Professor Zbigniew Asievich. And Professor Zbigniew Asievich was a very open person, and he likes everything new. He likes many mathematical theories and constructions, and in particular, Muffon loops and their properties and their applications to physics were also interesting to him. Maybe it was some influence of Professor Evgen Paal from Estonia, because there were some group of physicists. They worked in this area, Muffon loops, applications of Muffon loops in physics, and Professor Zbigniew Asievich worked at that time with Evgen Paal. And I will tell you about binary Lie algebras, but mostly I will concentrate in Maltsev algebras, which are in some particular Maltsev algebras. And the Maltsev algebras are the tangent algebras of smooth Muffon loops. Please, second page. Next page. So I will recall, it was in talk of Yakov Mostavoy also. I will recall the identities of which defining identities of Lie algebra, like x squared is equal 0 and Jacobian is equal to 0. In 1955, Maltsev, applying the Campbell-Hausdorff formula to the variety of analytic local loops, introduced some generalization of Lie algebras, so-called binary Lie algebras, as tangent algebras of analytic dissociative loops. And also he introduced a particular case of binary Lie algebras, Muffon Lie algebras, now called Maltsev algebras, as tangent algebras of analytic local Muffon loops. I will remark that dissociative loops, they are loops such that any two elements generate a group. And it is impossible to give the number of defining the identities of such a variety is infinite. But with algebras is different. As you see in my slide, the defining identity of a variety of binary Lie algebras is just x squared is equal 0 and Jacobian of x, y, xy is equal to 0. So it is only so two identities. And it was found by Gainov. On the other hand, the identities you see in my slide, x square equal to 0, and Jacobian of x, y, xz equal to Jacobian x, y, z and product to x times x, which define the variety of Maltsev algebras. In this form, it was found in the work of Segel, Arthur Segel. Okay, please, next page. So here is literature of all these identities and results. So Maltsev, it was done in 1955, Gainov in 1957, and Segel wrote the paper of Maltsev algebras in 1961. Thank you. So please, next page. Now I would like to give a definitions of quasi-groups, loops, and some related groups. So if let L be a set endowed with the binary operation, we define left multiplication like by this formula, LA to XS multiplication by A from in the left, right multiplication analogously, and quasi-groups, L with operation, with the binary operation is a quasi-group if the mappings L left multiplications and right multiplications are bijection for all elements of L. Also, it is we will define left multiplication group. It is a group generated by all left translation, left multiplication. Right multiplication group is a group generated by all right translations. And multiplication group of loop, of quasi-group, is a group generated by all left and all right translations. The quasi-group with identity element is called a loop. With loop, we can associate another group. Inner mapping group is a group of elements of multiplication group such that these elements fix identity. Left inner mapping loop. It is a subgroup of left multiplication group such that all elements fix identity element, and analogously right inner mapping group. It is subgroup of right multiplication group such that all elements of this subgroup fix identity element. Please, next page. And also we can introduce the family of mapping, like here L using element x and y. It is like some deviation of associativity Lx, y, Rxy, and also mappings Tx, depending only of one element, like conjugation in group theory. So these three families, all three families generated inner mapping group. And this family of this element L generated left inner mapping group, and family R generated right inner mapping group. As usual, a normal subloop is a kernel of loop homomorphism. This criterion is true. Subloop is normal if it is invariant under inner mapping. Please, next page. And in the theory of quasi-group and loops, it is interesting to consider some classes of loop, some important classes of loop. Loops, left ball loops. They are, here you see defining identity. So this three composition of this mapping is just one mapping, so one left translation. Right ball loops is analogously. Also, you can consider composition of R-arcs, right translation by X, right translation Y, and right translation by X, and all this composition is coincide with some right translation, right multiplication by some elements. A loop, which is a left and right ball loop simultaneously, is called a Muffang loop. Muffang loop has different, there exist different definitions, and the most common is this identity, one of the Muffang identities. So it is very close to associative law. And Muffang loops, first, it is well known that Muffang loops, Muffang loop is diassociative. It means that every two elements of this loop generate a subgroup, and Muffang loop possesses many properties common in like group. Please, next page. If we consider left ball loop with the property which called the automorphic inverse property, such a loop is called a left Bragg loop. And Bragg loop also is very important class. Class of Bragg loops is important class in loop theory, and in differential geometry. Analytic Bragg loops describe the symmetric spaces. Their tangent algebras are Lie triple systems. In other classes of loops, if we consider loop with the property that left inner mapping are automorphism of loop, such loop is called left automorphic loop. If we consider that all inner mappings are automorphisms of loop, such loop is called automorphic loops. For example, left Bragg loops are left automorphic loops. The theory of smooth ball loops and their tangent algebras was developed by Sabinin and Mikheyev in the 80s. Also, they found the defining identities of a tangent algebra of an analytic loop without any extra conditions. Now, such algebras are called Sabinin algebras. On the theory of smooth loop, left automorphic loops with additional properties and corresponding tangent algebras were their results of Tkk in 70s. And recently, this direction, the theory between tangent algebras and analytic Muffang loops and tangent algebras was continued over the class of commutative automorphic loops by Alexander Ryzhkov and Peris Izquierdo. Please, next page. So here I give the literature about the topics in the page before. So Sabinin and Mikheyev, 2 papers, one about the geometry of ball loops, infinitesimal theory of local analytic loops. Here is article of Michiko Kikawa about left automorphic loops, and recent article Grishkov and Peris Izquierdo. Please, next page. I will repeat the definition of defining identities of Maltsev algebra. So it is anti-commutative algebra with the identity such that Jacobian of x, y, product xz is equal to Jacobian xyz product with x. The tangent algebra of smooth automorphic move-on loop is a Lie algebra. And tangent algebra of a smooth left automorphic move-on loops is a Maltsev algebra with the following additional identity. Jacobian x, y, z, w is equal to 0. We will call this identity 1. And it is clear that this algebra obeys the identities of, it is Maltsev algebra with such identities. Identities number 2. It was found in 2004 with the article with my student Ramiro Carriota Catalan. Please, next page. We will call the Maltsev algebras with satisfying the identity, the property 1, Maltsev algebras of first type, and Maltsev algebras satisfying property 2, Maltsev algebras of second type. And this next theorem is true, that the varieties of Maltsev algebras of first type and second type are different. And there exists an example of the algebra, Maltsev algebra of second type of dimension 23, which is not algebra of first type. And open question arises if this 23 is a minimal dimension of example of this kind. And it is still is open question, but recently I received some message from Pavel Pasha Zusmanovich. He has some advance to show this result. And there exists also a free algebra of second type, which is not of a first type, of dimension 29. This example was found by Professor Shestakov. He uses a programmer of Albert. Please, second page, next page. So we understood that the first time is Maltsev algebras with defined of left automorphic move-on loop. So smooth loop, which correspond to Maltsev algebra of first type, is just smooth move-on loops with the property of left automorphic property. And so we ask ourselves what kind of loop, a smooth loop, correspond to Maltsev algebra of second type. And we got the following theorem. So we will let L be a loop such that every 3 elements of L generate a left automorphic subloop. We will call a loop L with this property an almost left automorphic loop. And so we have this theorem. A tangent algebra of a smooth almost left automorphic moving loop is a Maltsev algebra of second type with such definition. No, it is not. Sorry, second is different. It is first. Sorry, I should change this. The local moving loop which corresponds to the Maltsev algebra of second type is almost left automorphic. And here's literature. Please, we will not see again definitions. Maybe next page, please. And it was very long standing problem about speciality of Maltsev algebras. Maltsev algebras are related to alternative algebras in the same way as Lie algebras are related to associative algebras. If A is an alternative algebra, then the algebra A minus with the multiplication commutator like A by B minus BA is a Maltsev one. It was an open problem during many years whether the analog of Poincare-Birkhoff-Witt theorem is true for them. That is, whether any Maltsev algebra is isomorphic to a subalgebra of an algebra A minus for a suitable alternative algebra A. And such a Maltsev algebras are called special in literature. In 2017, Ivan Shestakov announced the existence of the example of non-special Maltsev algebra. But in our case, we think that Maltsev algebra with identity, so it is first type of the identity Jacobian x, y, product z by 2 by t is equal 0 are special. Please, next page. Also, the problem of it is known that moving loops could be extended by be global. So it is some for the theory of analytic moving loops in their tangent algebras, the existence of global moving loops was proved by Kerdman. So the theory is very similar, like it is in case of Lie groups and Lie algebras. And we proved that for subclasses of analytic moving loops, the questions of existence of a global left automorphic moving loop, which correspond to the given Maltsev algebra of the first type, is solved positively. Please, next page. To respect to the class of smooth left automorphic loops, also it's possible to generalize our results. We can consider following identity for the variety of Maltsev algebras. And in this case, also we can find that such a Maltsev, the smooth moving loops, which corresponds to our Maltsev algebra with the generalized identity, it is so, like here. So we will call this variety of K generalized left automorphic moving loops. And the tangent algebra of smooth K generalized left automorphic moving loops is an algebra from the variety like this, defined by our identity. And so it is the same theory of like in so the theorem is following. A local smooth K generalized left automorphic loop defines a global smooth K generalized left automorphic moving loops. And please, next page. I see that I have very little time, yes? So this is literature about analytic moving loop in the large by Kerdman, and about our specific case, it is this article. And please, next page. And so I will speak about moving theorem. It is very famous moving theorem. In 1935, Ruth Moving proved this theorem that the following property. If for some element ABC from moving loop, ABC generate a subgroup of M, if for some elements ABC, the associator, this is definition of associator, is equal 1, so these three elements generate a subgroup of M. And the dissociativity of moving loop, it is a very simple corollary of this property. And in this conference, Loops 11, it was Andrew Raha proposed the following question. We say that a variety V of loops satisfies the moving theorem if for every loop Q in V the following implication holds. For every X, Y, Z in Q, if they associate these three elements, then the subloop generated by X, Y, Z is a group. Is every variety that satisfies the moving theorem contained in the variety of moving loops? And it was before, please, next page. So it was found some single examples, not variety. So we began to think about variety, and we decided to go to variety of algebras. So we found the variety of binary Lie algebras, which satisfies the analog of this equation. So the equation is the following. If three elements of algebra such that Jacobian is equal of these three elements is 0 is satisfied, then the subalgebra of generated by this three element is a Lie algebra. And we so in the question if there exists a non-Maltsev variety, and we found the variety of binary Lie algebras satisfying the analog of moving theorem, which does not belong to the variety of Maltsev algebras. Please, next page. So this is the theorem, and we consider binary Lie algebras defined by the identities. X square is equal 0, anti-commutative, and this identity Jacobian of x, y, z u equal to 0. And then we proved that this variety is not necessarily a variety of Maltsev algebras, and second point that every algebra from B satisfies the analog of moving theorem. Please, next page. So
I think
here's the
time
example.
is
Maybe
very
I will not
limited.
give-
We must
explain this
conclude.
Yes, I will conclude. So we will, interesting also to study the properties of this binary Lie algebra, which appears in this theorem. And please, next page. And next page, so we show that we found this binary variety of nilpotence. See, we found this variety of binary Lie algebras with such a property which I announced with analog of moving theorem. Please, next page. And next page. This is literature about the topic. And please, next page. And I just will show you the. So it is known that for Maltsev algebras, also the Lévy-Maltsev theorem, it is like in theory of Lie algebras. So there exists such a decomposition of Lévy decomposition. And in general, for binary Lie algebras, it is not true. But for our case, in this particular case, for binary Lie algebras, which we described in previous page, which I described in previous page, this Lévy decomposition and Lévy-Maltsev theorem holds. It is. I will finish with this. Maybe next page, last page. Okay, and last page. Yeah, it is literature about this last property. Okay, thank you very much. I finish.
Thank you very much.
Your microphone is off. Okay, thank you.
So we move on to the next speaker.
Yes.
Okay.
The speaker is Tepiti Saho.
Yeah, Tepiti Saho. Yeah.
Hello.
Hello.
Am I audible?
Yeah, please share your screen.
Yeah, thank you.
Yeah. So the next speaker is Tepiti Saho, and the title is on the relative finite dimension in modules of rings. Okay, you can start.
Thank you. So myself, Tapati Sahu from Mahe, MIT, Manipal, India. And the title of my presentation is On the Relative Finite Dimension in Model over Rings. These are the keywords of my presentation, such as R module, R submodule, relative essential submodule, relative uniform submodule, theta direct, theta FGD, theta complement, and theta E irreducible. So I'll start with the definition of a left R module. An abelian group M plus is said to be a left R module where R is a ring if there exists a mapping which is called scalar multiplication from R plus M to which satisfy the following conditions, such as R into A plus B is equal to RA plus RB, R plus S into A is equal to RA plus SA, and R into SA is equal to RS into A for all AB belongs to M and RS belongs to R. These are some standard examples of a module. Every ring R is a module over itself. Every group is a module over the ring of integer Z. Every vector space over a field F is a module over a ring F. And endomorphism of an abelian group R plus over itself is an R module. A non-empty subset K of M is called R submodule or simply a submodule if xy belongs to K implies x minus y belongs to K, and x belongs to K, R belongs to R implies Rx belongs to K. A non-zero submodule K of M is called essential in M if K intersection A is equal to 0, where every submodule A of M implies A is equal to 0. If K is a submodule of M and K is not equal to M, then we say that M is a proper extension of K. And if every non-zero submodule of M is essential, then we say that M is uniform. Here is the definition of finite Poldy dimension. M has finite Poldy dimension if M does not contain a direct sum of infinite number of non-zero submodules. More precisely, M has FGD if for any strictly increasing sequence H0, H1 and so on of submodules of M, there is an integer I such that for every k greater than equal to I, Hk is essential submodule of Hk plus 1. In any module M with FGD, there exist non-zero uniform submodules U1, U2, Un, whose sum is direct and essential in M. The number n is independent of the uniform submodules, which is called dimension of M. If M has FGD, then every submodule K of M has also FGD, and the dimension of K is less than equal to dimension of M. If I and J are submodules of M, and I is maximal with respect to I intersection J is equal to 0, then we say that I is the complement of J. A submodule H of M is called E irreducible if H is equal to K intersection J, where K and J are submodule of M, and H is essential in K implies H is equal to K or H is equal to J. This remark says that every complement submodule is irreducible, but the converse may not be true. We can see the example Z12 over Z. If we take the principal submodule generated by 2, it is irreducible submodule, but it is not complement as K intersection J is non-zero for every non-zero submodule J of M. Now we define relative essential in a module M. A submodule H of M is said to be relative essential in M if there exists a proper submodule theta of M such that H is not contained in theta, and for any submodule K of M, H intersection K is contained in theta implies K is contained in theta. We denote it by H is theta essential in M, and if H is theta essential submodule of M and H is not equal to M, then we say that M is proper theta essential extension of H. M is said to be relative theta uniform if for every submodule K of M, K not containing theta, then K is theta essential in M. Now a submodule H1 of M is relative uniform or theta uniform if for any submodule H2 of M which is contained in H1 and not contained in theta, then H2 is theta essential in M. Let I be a submodule of M and theta be a proper submodule of M, then I is theta uniform if and only if for every submodules H1, H2 contained in I, H1 intersection H2 is contained in theta implies any one of them should contain theta. Here in these examples, we show that the existing essential, how it is different from the defining theta essential. For example, here R is equal to Z12 and M is equal to R, that means itself over itself. Then the submodules are as follows. Then H4 is S3 essential in M, but H4 is not essential in M. Similarly, H1 is S3 uniform, but not uniform in M. In the example 2, we have H2 is F3 essential in H4, but H2 is not essential in H4. Similarly, in the example 3, we can see the direct product of Z8 cross Z3 and R is equal to Z. Then we are taking theta is equal to Z8 cross 0. It's a submodule of M. Then the submodule 2 cross Z3 is theta uniform but not uniform. Now we define relative finite dimension in our module. So we start with the definition of theta direct. Let theta be a proper submodule of M and II be the family of submodules of M containing theta, then we say that II is theta direct if II intersection with sum of ij, where j is not equal to I, is contained in theta. And M has theta LGD if M does not contain an infinite number of submodules, Hi, not containing theta, with sum is theta direct. Here is one lemma which says that if M has theta LGD, then every submodule H not containing theta of M contains a theta uniform submodules. Here we show the proof. Let I and j be the submodules of M and theta be a proper submodule of M. If I is contained in J and J is theta uniform, then I is also theta uniform. Let Hi be submodules of M and theta be a proper submodule of M. When H1 is theta essential in H3 and H2 is theta essential in H3, and we have H1 intersection H2 contained not containing theta, this implies H1 intersection H2 is theta essential in H3. And if H1 is contained in H2 contained in H3, then the transitive law follows. Here is the proof of the first one. If theta is properly contained in Li containing Ki, the submodules of M such that K1 intersection K2 is equal to theta, then Li is theta essential in Ki for all I is equal to 1, 2. If then only if L1 plus L2 is theta essential in K1 plus K2. Now we can generalize K2 for n submodules. Let theta be a proper submodule of M. If M has theta FGD, then there exists theta uniform submodules, theta properly contained in Hi, such that their sum is theta direct and theta essential in M. This integer n is independent of the theta uniform submodules, which is called as theta dimension of M. If the submodule H of M is theta uniform, then the dimension will be 1. Here we are showing some examples where we got M has theta FGD, but M has no FGD. Where theta is equal to H4 we have taken in the example 1. Similarly, in example 2, we have shown that M has theta FGD, but M has no FGD. Here we are showing that the submodule H has theta FGD. Now coming to the definition of relative complement of H, let H be a submodule of M, then in submodule H dash of M is called relative complement of H if there exists a proper submodule theta of M such that H dash is maximum with respect to H intersection H dash is contained in theta. In this case, we say that H dash is the theta complement of H. Let A and theta be the submodule of M where theta is proper. If B is contained in theta, is the maximal among the submodules of M such that A intersection B is contained in theta, then A direct sum of A plus B is theta essential in M, and P is theta complement of A. Here is your proof. Let theta be a proper submodule of M if H and K are submodules of M with H intersection K is equal to theta, then theta dimension of H plus K is equal to theta dimension of H plus theta dimension of K. This is one corollary which follows from the lemma. This is for N submodules. Let theta be a proper submodule of M and theta dimension of M is equal to N. Then for any submodule H of M, H is theta essential in M if and only if theta dimension of H is equal to theta dimension of M. Let theta be a proper submodule of M and theta dimension of M is equal to N. Then for any submodule H of M, if theta dimension of H is equal to theta dimension of M, if and only if H contains a direct sum of n theta uniform submodules. Let theta be a proper submodule of M if M has theta FGD and H with a submodule of M with dimension of H is less than theta dimension of M, then there exists theta uniform submodules A1, A2, AK and so on, such that H plus A1 plus AK is theta direct and theta essential in M. Moreover, K is equal to theta dimension of H, M minus theta dimension of H. Suppose M has theta FGD and K1 and K2 be the submodules of M such that K is equal to K1 intersection K2 and K is the theta complement contained in theta, then theta dimension of K1 plus K2 is equal to theta dimension of K1 plus theta dimension of K2 minus theta dimension of K. This is the proof. Now we define theta E irreducible. A submodule L of M is said to be theta E irreducible if L is equal to K intersection H, where K and H are submodules of M, and L is theta essential in K implies L is equal to K or L is equal to H. When theta is equal to 0, we call it as E irreducible. This example shows that, here this K is theta E irreducible, but it is not irreducible. Now consider the submodule A, B, C of M. Then direct sum of A plus B is theta essential in direct sum of C plus B. Then A is theta essential in C, where C is the theta complement submodule of A. So suppose M has theta FGD, and if K is the submodule of M, then K is theta complement submodule if and only if K has no proper theta essential extension. This is the proof. This remark says that every theta complement submodule is theta E irreducible, but the converse will not be true. We are proving that every theta complement is theta E irreducible. And for the converse not true, we are giving the example Z12 over Z. If we are taking K is equal to T, we are constructing 2 generated by 2. We are constructing this as suppose K is theta essential in I and K is equal to I intersection J. And let K is not equal to theta, then I is equal to Z12. and k is equal to z intersection j, this is equal to j, then k is theta e irreducible, but it is not theta complement by the above proposition. Let k and theta be submodels of M such that theta is properly contained in k, then the following three conditions are equivalent. That is, k is equal to M, or k is not theta essential in M, but it is theta e irreducible submodel. K has no proper theta essential extension. K is a theta complement. Here, first we prove 1 implies 2, then 2 implies 3, then 3 implies 2, and 2 implies 1. Now from the theorem, the corollary follows. Let K be an theta e irreducible submodel of M, then K is theta essential in M, or K has no proper theta essential extension. K is theta essential in M, or K is theta complement. If M has theta FGD with theta dimension of M is equal to N, and H be a submodel of M, then H is theta essential in M if and only if theta dimension of H is equal to theta dimension of M. Here we are proving this result. Let M1, M2, Mn and H1 is to Hn be submodels of M such that M1 plus M2 plus Mn is theta direct, and theta is contained in Hi, contained in Mi. Then sum of Hi is theta essential in sum of Mi if and only if each Hi is theta essential in Mi. Let M be an R module and with theta FGD, and let K be a submodel of M says that theta dimension of M is equal to theta dimension of K plus theta dimension of M by K, then K has no proper theta essential extension in M. This is the proof. We are proving it by contradiction. First, we are taking K is theta essential in K dash. And here we are getting a contradiction that dimension of M by K is greater than equal to 1 plus dimension, theta dimension of M by K. This is a contradiction. If M has theta FGD and K is an theta E irreducible submodel of M, then M by K has theta FGD and theta dimension of M by K is less than equal to theta dimension of M. This is the proof. So in this presentation, we have given some characterization of finite dimensional vector space. For further work, we can work on this spanning dimensional aspects of our modules. These are the references. Thank you.
Thank you very much. In fact, you finished exactly on time. So I think we should achieve, provide you with an award.
Excellent.
For being the first speaker to end that time. Also, I wanted to remind participants to use Q&A or if you're panelists to use chat to ask questions of the speakers.
So should we move on to the next talk?
Yes, let's move on to the next speaker.
Okay, the next speaker is Harishana Panaka. The title of his talk is a review on the recent developments in probabilistic norm spaces. So please.
Yes, thank you.
Thank you.
Am I audible to you?
Yeah, you can share your screen.
Yes, sure. Thank you.
I just want to note one thing, that our question and answer box is still unavailable, at least to me. There is no way to ask a question.
Okay. Here I would like to give a brief review on the recent developments in probabilistic norm spaces. And I dedicate this presentation to Professor Moshevich. And first of all, I would like to thank Professor Hilda, for giving this opportunity to present this talk. So first of all, I would like to tell a familiar definition about distribution function. Distribution function is a mapping from extended real line to the closed interval 0, 1, satisfying these properties. That is, at minus infinity, it should take value 0, and at plus infinity, it should take value 1. And the function is non-decreasing and left continuous on R closure, that is the extended real line. And some of the particular distribution functions we need in this discussion is epsilon suffix a of x, defined in this way, and epsilon infinite of x, which is defined, which takes value 0 if x belongs to minus closed interval minus infinite, and 1 if corresponding to x equal to infinite. And we denote the set of all distribution functions by capital delta, and capital delta plus is nothing but those distribution functions takes value 0 to 0. And one can easily see that these two spaces, that is sets delta and delta plus, are partially ordered sets with respect to the partial order defined like this: f less than or equal to g if and only if f of x less than or equal to g of x for every x in the extended real line. And with respect to this partial order, one can see that the distribution function I told in the previous slide, that is epsilon infinite, will be the minimal element for both delta and delta plus, and epsilon minus infinite will be the maximal element of delta, and epsilon naught is the maximal element of delta plus. So we need an important condition to proceed further. If you take two distribution functions f and g, and corresponding to h belongs to open closed 0, 1, we are denoting the condition by this triplet fg semicolon h. It is nothing but f of x minus h less than or equal to g of x less than or equal to f of x plus h for all x belongs to this interval. So the main aim at first is how to make this distribution space metrizable. So there are several ways of making it into metrizable. One of the metric we are interested is Sibley metric, that is denoted by d suffix s. So how we are defining the Sibley metric is d suffix s of f comma g is nothing but the infimum of h belongs to open closed 0, 1, such that this two condition holds. This condition is already mentioned in the previous slide. So some of the terminologies we need to just define the notion of probabilistic norm spaces. The first one is triangle function. Triangle function is a binary operation defined on the space delta plus, and satisfy this condition, the mapping should be commutative, associative, non-decreasing in each place, and it has an identity epsilon naught. And triangular norm in short, we are telling it as T norm. It's also a binary operation on closed interval 0, 1, satisfying the properties. It should be commutative, associative, and tau of xz less than or equal to tau of yz whenever x less than or equal to y, and tau of x1 equal to x. And if you look at the continuity of a triangle function, which means that the continuity with respect to the topology of V convergence in delta plus. And some of the typical triangle functions are convolutions. So these are the two typical continuous triangle functions we need in the further discussion. That is tau suffix capital T of f comma g of x, which is defined in terms of supremum, and tau suffix tau star of f comma g in terms of infimum. So here tau star is a continuous T conorm, namely a continuous binary operation. What I'm just giving a definition for T conorm. It is nothing but a continuous binary operation on closed interval 0, 1. And how we are defining the T conorm is, to define a T conorm, you need a T norm with you. It is nothing but 1 minus T of 1 minus x, 1 minus y. So now I'm giving some examples for T norms and the corresponding T conorms. For example, if you take the T norm as minimum function, then the T conorm will be, the corresponding one will be maximum. And if you take the product function as the T norm pi of xy equal to xy, then the corresponding T conorm will be defined in this way. So there are some interested other T norms and T conorms mentioned here. So what one can see is the set of all T norms is a partially ordered set with respect to the pointwise partial ordering of functions. And with respect to that partial order, one can see that the relation between the minimum norm and product norm and the Darson norm, that is W, is in this way. So moreover, you can see that the T norm M is the maximal T norm because minimum of x and y less than or equal to maximum of x and y for all x, y in closed interval 0, 1. And with this, one can conclude that if any T norm will be less than or equal to its T conorm. So if you take the set of all triangle functions, one can see that it's a partially ordered set with respect to the partial order defined in this way. There is T1 less than or equal to T2 if and only if T1 of f comma g less than or equal to T2 of f comma g for all f and g from delta plus. So from here, one can tell that for every continuous T norm, capital T, and a continuous T norm T star, one can tell that the typical triangle functions based on the convolution, that is tau suffix T and tau suffix T star, will satisfy this relation. So next question is, when one can tell a T norm tau is said to be Archimedean. One can tell that a T norm tau is said to be Archimedean if the corresponding conorm, that is T star, admits no idempotence other than epsilon naught and epsilon infinite. Then we will say that such T norms are Archimedean. So now I will come to the one of the main terminologies using here, that is probabilistic metric spaces. Probabilistic metric spaces were introduced by Carl Menger. He introduced this idea of statistical metric by replacing our usual metric, the number d of pq, which basically gives the distance between the 2 points p and q, to a non-empty set, in a non-empty set S, with a distribution function f suffix pq. F suffix pq means f suffix pq of t corresponding to t belongs to 0, infinite. What does it mean is, it represents that the probability that the distance between the points p and q is smaller than t. So instead of representing the metric as a number, he is representing it as a distribution function. So formally, this is the definition of a metric space. You take a non-empty set S, a function f from S cross S to delta plus, and tau is a triangle function. Then if these conditions are satisfying, then we will tell it as a probabilistic metric space. So from this, the notion of probabilistic metric space, he had defined the notion of probabilistic norm space in this following way. So you take a vector space V and two continuous triangle functions tau and tau star, and the mapping V from V to delta plus. Normally we know that the concept of norm is a real valued function. Here it is not a real valued function, it is a function from V to a collection of distribution functions. So satisfying these conditions, that nu p should be equal to the distribution function epsilon naught if and only if p should coincide with the null vector in the vector space, and nu suffix minus p should be equal to nu suffix p. And the third condition is somewhat similar to the triangle inequality in our usual norm. If these four conditions are satisfying, then we are telling this mapping nu is a probabilistic norm. And if you choose the triangle functions tau and tau star in this way, that is, I have told that the two continuous triangle functions using convolution, that is tau suffix t and tau suffix t star, corresponding to some continuous t norm tau and its corresponding t conorm tau star, one can tell that this quadruple, which we can denote it by the triplet V nu T, that is called a Menger PN space. PN space is the abbreviation of probabilistic norm space. So these are the good examples for a probabilistic norm space. You take a usual norm space in which, with respect to that norm defined on the usual norm space, one can define a probabilistic norm mu suffix p in this way. And the corresponding triangle function, you have to take it in this way. Then one can verify all the conditions of a PN space here. So similarly, this is the another example for a probabilistic norm space. Example 3 is also another example for probabilistic norm space. So in the norm space definition, if the mapping nu satisfies the conditions from n1 to n3 except n4, the n4 scaling condition is, if you are replacing with this condition, then such spaces, PN spaces, are called Sturgeon space. So if you have a probabilistic norm space, then one can construct a metric on that probabilistic norm space. So that means I can tell that every probabilistic norm space is a probabilistic metric space. How can we define it? It is in this way. So you have a PN space V with you. You can define a probabilistic metric F on V by F of PQ is nothing but nu suffix P minus Q. So it will satisfy all the conditions of a probabilistic matrix. So from this, one can conclude that every probabilistic norm space is a probabilistic metric space. So how to define neighborhoods in a PN space? We can define it in this way: n suffix P of t equal to set of all Q in the underlying probabilistic norm space P, such that nu suffix Q minus P of t is greater than 1 minus t. And this neighborhoods determines the topology on this probabilistic norm space, that is called the strong topology. Sorry. So in probabilistic norm space, one of the major question was, can we make a probabilistic norm space to be a topological vector space? So to get the probabilistic norm space to be a topological vector space, we need to verify that the operations mapping addition and scalar multiplication must be continuous. And what we can see is the first two mappings, this PQ going to P plus Q, it is uniformly continuous, and P going to alpha P, it's also continuous. But we cannot tell in general this will be continuous in a PN space. So to justify that one can see this example. Earlier I had given one example 3. In that example, if you take a sequence in this way, one can see that this mapping alpha going to alpha p is not continuous. So that means this example justifies that every Pn space is not a topological vector space. So obviously our aim is to check under what condition we can make it as a topological vector space. So we had found that the sufficient condition for this mapping to be continuous is the underlying triangle function tau star should be Archimedean. Under that condition, we can verify that the Pn space will be what? A topological vector space. So if you take a Pn space V and the underlying triangle function is continuous, tau is continuous, then the strong neighborhood system determines a Hausdorff topology on that Pn space. So these are the analogous definition of the convergence of a sequence and Cauchy sequence and distributionally compact in a Pn space. So due to the time restriction, I am skipping these definitions. So one of the important result here comes here is if you take a Pn space V with the triangle function tau continuous and together with V, you take the strong topology and you take delta plus the space of distribution functions together with the topology obtained by the Sibley metric. And I'm taking the Cartesian product of V and B together with the product topology. Then one can see that the operations addition on V is jointly uniform continuous map from V cross V. With respect to that operation, the pair V with addition is a topological group. So here comes the main result. That is every Pn space in which the triangle function tau star is Archimedean is a topological vector space. Earlier I told that the necessary sufficient condition to become Pn space to be a topological vector space is tau star is Archimedean. So this example will justify the above theorem. So next, if you take a probabilistic norm space V, we can tell that it is distributionally bounded. Debounded means distributionally bounded. If its probabilistic radius, we are denoting it by R suffix A, should belongs to the distribution functions collection D plus, where how we are defining Ra of X is, which is defined in this way. The left limit of infimum of nu P of X such that P belongs to A corresponding to all X in this interval, and the radius will take value 1 if X is equal to plus infinite. So these are the results related to distributionally boundedness of a Pn space. If you take a subset of a Stirner space P, then that subset E is distributionally bounded if and only if it is a bounded set. And the next result says that if you take a T1 topological vector space and it is normable if and only if there is a neighborhood of the origin theta. Theta means it is a 0 in that underlying vector space that is convex and topologically bounded. So the next result introduces a general class of probabilistic norm space which are not of Stirner's type. So here this result says that if you take a Pn space V with a non-Archimedean triangle function tau star, and if you take any two functions f and g satisfying these two conditions, that is f is the right continuous non-increasing map going from 0 closed interval 0 plus infinite into 0, 1, and if satisfy the condition f of 0 equal to 1. And the second function g is a map from r plus cross r plus into 0, 1, and it is continuous in the first and in the second places. And this mapping g is non-decreasing in the first place and non-increasing in the second place, together with the condition g of x0 equal to 1. Then we can define a norm on V as below, that is nu from V to delta plus by nu P of x is equal to f of norm P and g of x comma norm P. Then one can see that this quadruple V nu tau star, it is a topological vector space, and this quadruple is not a Stirner space, and it is not a strict PN space, and one can see that it is normable. So this theorem gives a new class of PN spaces which are not of Stirner type. So to justify this result, we have one example. You take a non-empty, vector space B together with new norm defined in this way. So underlying V, we are taking it as a norm linear space. V nu, and the triangle functions we are taking pi suffix pi and pi suffix m. Then with respect to this norm, one can see that this is a PN space, and which satisfies this condition, that is, this quadruple is not a PN space of Stirner type, and this quadruple is a topological vector space, and it is not a strict PN space. And finally, one can see that this quadruple is normable. So this example justifies the above theorem, and the above theorem gives a new class of probabilistic norm space which are not of Stirner type. So these are the major references. One can see that the recent developments of this probabilistic norm space in this first textbook, and some part of this presentation, it is published in this last paper. So with this, I will conclude my session. Once again, I would like to thank Professor Hilda for giving this opportunity. Thank you.
Thank you.
Thank you.
Thank you. You finished 5 minutes early. So we can move on to the next talk. The speaker is it's a very long name. Malina Recon. Hello, are you there?
Hi.
Oh, hi. I don't know how to pronounce your name. Can you pronounce it?
It's very long. It's Guadalupe Rafael Molina Rincon.
Oh, okay. Thank you. Okay, you can share your screen with us.
Okay. Is it okay?
Yeah, okay.
It looks okay?
Yeah. That will be the screen of your whole computer. Yeah. Okay.
Okay. Is it okay now?
Yeah, it's okay. Yeah.
Perfect. So
yeah,
everything is okay?
Yeah. Okay. You may start.
Okay, perfect. Okay, so well, first of all, I would like to thank to the organizer of this Congress because they invite me. So I remember Zbigniew. I talk sometimes with him, and I remember that he had a very eclectic way of thinking. So this presentation is inspired on that. So, well, the idea of this presentation is to apply the theory of random graphs to Leavitt path algebras. So that's the title of this presentation. First, I'm gonna introduce the concept of Leavitt path algebras. I will give some motivation, and then I will I will explain several things. These slides are very detailed, so if you cannot follow them completely, don't worry. In the top part of each slide appears my email, so if you want slides, I can email a copy for you. So I'm going to start. If C is the field of complex numbers and S is the rank of infinite matrices over C, then the invariant basis number property tells us that if we take the direct sum of C twice, this sum is a vector space over C and is not isomorphic to C. However, if we try to do the same with the ring of infinite matrices, we have that if S, some direct sum with S is isomorphic to S, all that as free modules. This property, so for example, a question that can come up is if there is a ring that can interpolate between these two cases, no, between the case of vector spaces and the case of the ring of infinite matrices. And one answer to that was precisely what is called now the Leavitt algebras. An example of that is given in this example. And I think it was the first one of this kind. One interesting property of the Leavitt algebra is that this can be generalized, and we can associate Leavitt path algebra to every directed graph. On the other hand, we have the Cons algebra, which was introduced by Cons himself. And that in that algebra, we have that is a C-star algebra, and the Leavitt algebra given in the example, in the previous example, can be embedded in the Cons algebra in a very nice way. That property is not just a causality, because the Cons algebra can be further generalized to what is called graph algebras. Those graph algebras, just as the Leavitt path algebras, they are algebras that are associated to directed multigraphs. And they have the very nice property that the Leavitt path algebras can embed very nicely in the graph algebras. That means if I have a directed graph and I take its Leavitt path algebra, then that Leavitt path algebra can embed nicely in the graph algebra corresponding to the same directed graph that is under consideration. Graph algebras are important because they can realize several quantum structures. For instance, they can realize quantum spheres, quantum projective space, and quantum complex projective spaces. So, moreover, if for several properties can be described, For example, if we want to know if a graph algebra is simple, then that graph algebra is simple if and only if its corresponding Leavitt path algebra is also simple. So another example of that kind of properties is the K theory that corresponds to the graph algebras. For example, the group K0 is isomorphic to the group K0 associated to the Leavitt path algebra. So they share several properties, and because of that, the Leavitt path algebras can be very interesting to study. In order to continue the talk, we have to review several concepts of graph theory. I defined a directed multigraph in the natural way. We can see an example here. We have vertices, we have edges. The edges are oriented. I defined what is a sinc vertex. This is an example. That means that no edge comes out of the sinc vertex. On the other hand, we have the source vertex. That means that it's a vertex that doesn't have arrows coming out of it. We have several definitions that are very used in graph theory, like a path. A path is a sequence of edges in this way. A simple closed path can be something like this, a cycle, and a cycle with exit. We have the cycle and then the exit. So this is very, very easy. An infinite path is a sequence of edges of this shape. And particularly, we can also have, in the case of a cycle or a simple closed path, also we can have we can have infinite paths. No, that means we go around the cycle several times, and that way we can get infinite paths. Similarly here with any closed path. So in this way, we can go several times. On the other hand, we have that graph will be called cofinal if given a vertex, we can't, or given any vertex of the graph, we can reach any other vertex that resides in a cycle, or we can get a path from any vertex to a sinc if there is a sinc in the graph. For example, we have here an example of a graph that is cofinal. In this case, all the vertices of the graph reach the cycle, and there is not any sinc in the graph. There is, however, a source. On the other hand, we have this graph that is not cofinal, that we have a cycle here, and we have a sinc here, but we cannot go from the sinc to the cycle again. So this graph is not cofinal. We have we defined an acyclic graph as a graph that doesn't have directed cycles. A property of a graph being cofinal is that if it has a sinc, then that will be the only sinc in G. And on the other hand, if it has a sinc, it has to be acyclic. So for example, in this case, we have two acyclic graphs. One has just one sinc. So this graph will be cofinal. However, this one is not cofinal because it has two sincs. So if a graph has a sinc, has to be acyclic. That means doesn't contain any cycle, and that's it. A directed multigraph is irreducible if we can reach, given two vertices on the in the graph, we can go from one vertex to the other and in the other way around. That implies that, for example, in this case, if we consider this vertex and this other vertex, we can go from here to here. Vice versa, we can go from this vertex again back to the original vertex. A graph is primitive if the greatest common divisor of the length of the closest paths is 1. The set of all primitive directed simple paths will be denoted by Pn. So in this case, we have a graph that is not primitive because the greatest common divisor of the length of the closed paths is 3. The adjacency matrix of G is defined in the natural way. So for example, in this case, we have this graph and there is an directed edge from 1 to 2. So we have a 1 here. On the other hand, we have 2 directed edges from 2 to 3. So we have a 2 here. And if we proceed in that way, we can get all the adjacency matrix. The extended graph of a directed graph is just to add for each edge the edge that goes in the other way around. So for example, in this case, if we consider this edge, E21, then we have E21 star, that is the edge in the opposite direction. No? If we proceed in that way with all the other edges, then we will get something like this. So the graph with all these new edges is the extended graph. And the extended graph implies, well, a way to define that the directed graph is connected is if we can find a path in the extended graph between any 2 vertices. Now we have the definition of a Leavitt path algebra. The Leavitt path algebra is defined in this way. An easy way to define the Leavitt path algebra is just to consider the path algebra implied by the extended graph of a directed graph G. And then we make the quotient with the ideal generated by the relations of CK1 and CK2. So we have a very natural way to define the Leavitt path algebras. An example of the, well, this is the example that I gave at the beginning, but in a general way. In the beginning, I gave the example of LK13, and this is for any n. So this is an example of Leavitt path algebra. And if we consider, for example, the graph of the rows with n petals, that is this one, that means that we have n edges all around, then we have that the Leavitt path algebra, this one, is isomorphic. Well, the Leavitt path algebra of the rows with n petals is isomorphic to the Leavitt algebra, this one. Another example is if we take the case of just one loop here. In that case, the Leavitt path algebra is isomorphic to the algebra of Lorentz polynomials. And if we consider the Leavitt path algebra of a path of length n, then the Leavitt path algebra is isomorphic to the matrix algebra. And nice property of the Leavitt path algebras is this one. This is it can be generated in this way. And if we take this, well, the definitions are valid for any kind of directed graphs, in particular for disconnected graphs. So if we have a disconnected graph, then the Leavitt path algebra of the disconnected graph is isomorphic to the direct sum of the corresponding Leavitt path algebras. So for example, if we consider the disjoint union of two Leavitt path algebra associated to AM and AN, that means two different matrix algebras, then the corresponding Leavitt path algebra would be isomorphic to the direct sum of those algebras. Now, here we just defined the a ring is said to be simple if it doesn't have two-sided ideas, just non-trivial two-sided ideas, just 0 and the whole ring can be two-sided ideas. The idempotents are orthogonal if this property is satisfied, and an idempotent is said to be infinite if there exists orthogonal idempotents f and g such that E is equal to f plus g, where g is distinct to 0, and this property is satisfied. A ring is called purely infinite simple if every non-zero one-sided idea of R contains an infinite idempotent. So in few words, the idempotent E is infinite if R is isomorphic to a proper direct sum of itself. Now we have some theorems that are very important in the theory of Leavitt path algebras. We have the Simplicity Theorem that says that a Leavitt path algebra is simple if and only if the directed multigraph is cofinite. That means that is something like this. And satisfies condition L. That means that we have a cycle with exits. If we, so G satisfies condition L if every cycle of G has an exit. We also have the purely infinite simplicity theorem, which says that if the Leavitt path algebra is simple and it contains at least one cycle, then it must be purely infinite simple. We have a very nice theorem that is the dichotomy principle that says that every Leavitt path algebra that is simple is matricial or is purely infinite simple. So, and additionally, we have the finite dimensional theorem that says that if the Leavitt path algebra is finite dimensional, then that implies that the directed graph on which it is based on is acyclic, and therefore we have that the Leavitt path algebra has to be isomorphic to a direct sum of matrix algebras. We have that, well, now what I am gonna try to do is that the theory of random graphs for the case of directed graphs is not very extensive. So what I am trying to do is to try to use the theory of random graphs, simple, traditional random graphs, and apply it to the case of the algebras. In order to do that, we have to assign to a simple graph a directed graph. And there are several ways of doing that, but the way that I use is the one defined by theorems, and is the one that I am going to describe. So first, I'm gonna make a review of some definitions in the case of simple graphs and multigraphs, not directed ones. So first, we have multigraph is just something like vertices and edges, but the edges are not oriented. The degree is just the number of edges that are incident in the vertex that is under consideration. In this case, for example, if we take the vertex 2, then this vertex has degree 4. Similarly to the case of directed multigraphs, we have a path, we have closed paths, cycles, and we say that multigraph is connected if, similarly to the directed case, we can go from one vertex to another vertex using a path of edges. We have some cases of multigraphs. One case is a tree graph. That means that doesn't have cycles. And the unicyclic graph, that means that we have just one cycle. In this case, in the unicyclic graph, is just a tree plus one edge. Always will be something like that. An observation that is important to some of the terms that I will give is that any tree will have at least 2 leaves. A leaf is a vertex with degree 1. So in this case, we have 3 leaves, and this one, 4. And we have also another property that if we have a connected multigraph with at least 2 cycles, and we have these 2 cases, that means and this one is a subgraph of the graph under consideration, or this one. In this case, for example, we have 2 cycles because we have a diagonal. This, in this case, and it's just to describe the idea, but in the general case, we have a cycle and we have a path going from one vertex of the cycle to another vertex of the same cycle. On the other hand, we have the 2 cycles can be connected by a path, just like in this case. And we have also another observation. If we have a graph whose maximum degree is less or equal than 2, then we have just these 2 cases, or it is a path if it is connected, or it's a cycle if it is connected. We can have also the case of disjunct unions of cycles and paths. We have a spanning tree. That means that a tree that contains all the vertices of a graph. And we have that graph is unicyclic and has minimum degree 2, then it has to be a cyclic graph because we have just 2 possibilities, the path or the cycle. And I am gonna define something that are called the congraphs. Congraphs is just basically a graph plus one universal vertex. In this case, the universal vertex is asterisk. And this asterisk is connected to every other vertex of the graph. So universal vertex is a vertex that is connected to every vertex in the graph except itself. So we have here an example, and I'm gonna be using these graphs because I need one property in order to get results. I need that at least every vertex has to have degree at least 1. So that's why I define these graphs.
We have 5 minutes left.
Perfect.
Yeah.
So in view of that, I defined the cone graph, which I denote by G delta, G triangle. And then I associate a directed graph to those cone graphs. The directed graph that I associate is defined by avoiding what is called backtracks. In this case, for example, a backtrack is I take this way, and then but I cannot go back using this other edge. However, I can use other edges. So we have and we defined the edge matrix exactly by defining an edge will be a vertex, and I can go around I can go from one vertex to the other if the edges are connected in the correct way. So in that way, one of the interesting properties of the oriented line graphs is that if the graph has a cycle, then the oriented graph has to have a cycle. That property is if and only if. That means that if the graph doesn't have a cycle, then the oriented line graph doesn't have a cycle neither. That means it's acyclic. So, and another interesting property is that if I have a vertex of degree 1, then the directed graph OG will have sinks and sources. So for example, this is a very important property that the oriented line graphs always, if they satisfy certain conditions, then there will be always an exit for every cycle in the graph. The main theorems is that the Leavitt algebra is finite if and only if G is a forest in the case of an oriented line graph associated to the graph. And it's simple. It's purely infinite simple if the graph has minimum degree 2 and at least has 2 cycles and is connected. That will help to define the random case. So I defined a random graph in the natural way. I have an example here where each of the cases has the assigned probability. So if I choose randomly a graph of these ones, then we get a random graph. By associating the directed graph, we can also consider the case of the cone graphs, that is just a natural extension of the simple case. And if we can also define random directed simple graphs in the case of probability equals 1/2, then we have the uniform case. In that case, we have this theorem which says that almost all the directed simple graphs are primitive, but using the theorems that we checked before, we can get that then almost all the Leavitt path algebras induced by these graphs are simple. So we have that in the case we have this theorem that almost all the directed simple graphs induce Leavitt path algebras are purely infinite simple. This is the most general theorem. And one more restricted result is this one, that almost all oriented line graphs associated with cone graphs induce Leavitt path algebras that are purely infinite simple. So this result, even though it's more restricted, is interesting because it helps us to transport several of the results of random graphs to the case of Levi-Path algebras. We have all the regularity conditions that are needed are satisfied by these graphs, so we don't have any problems. So in particular, we can transfer results of phase transitions and define those results for the case of Levi-Path algebras. That is something that I am doing at this moment. So, and well, if you are interested in this presentation, this was very fast, but if you want the slides, you can send me an email and I will be posting a paper in the archive in the coming days. So if you want to know about that, just also, you can write me an email. So thank you, and that's it.
Okay, thank you. Okay, the next speaker is Fernanda Azarita.
Yes, I'm here. I don't know if you can see me.
I cannot. Oh, okay.
Hello.
Hello.
Yes, we have your main computer screen, but not the slideshow.
Oh, yeah. Okay.
Okay. Okay.
Now we have your video.
Okay, then I will put the slide here. Share screen.
Share your screen.
I guess now you can
Yes, that's
see the slides. Yes?
Yes.
Is it okay? Okay, wonderful. Okay, thank you very much for the invitation. I want to share with you some very simple ideas on gravitational waves, which are based on many ideas of Zbigniew. And well, and to tell you on these ideas, I want to start on how I met him some years ago. I knew him the year 2010 in this conference, but in Nayarit. I was a student and it was a bit strange for me. It was like a conference in a rainforest there. And when I got to the conference, there was someone starting something, some talk on gravity with this typical equation here. And then I saw Zbigniew very angry with this expression. He was very excited, saying it was wrong, actually, to write that it is in almost every book on general relativity. And he was so excited that he took a marker and he made a very big X on that equation. It happens that he didn't realize that it wasn't a whiteboard, but it was the screen. It was the screen for the projection. So we have many talks with this giant X there, and I was very terrified there, because I had to talk about gravity, and I was thinking, my God, what will happen with me? And then I decided, okay, people here don't like metrics, so I made a very good decision then, and I changed all the expression with metrics to differential forms to the language of the Vielbein and the spin connection. And when I give this talk, there was no problem. And Zbigniew was happy with it. But afterwards, I was a very young student, and I asked him, well, what was wrong with this typical equation that appears in every textbook on general relativity. And he told me, look, everybody doing a mistake does not make that mistake right, okay? And it happens that you have to decide, are you talking about one form of length on a line, or are you talking about a tensor on a four-dimensional space-time? And he told me, well, I know what physicists mean with that, and it is a very vague idea about how you could make a pullback of this metric on a four-dimensional space to align to define a one form of length. But if you are talking about a map, then you should state the domain and the codomain of that map. So this expression there is not a good way of defining a length, neither a good way of defining a tensor, and neither a good way of defining a map. So it is wrong. And then I realized he was completely right. And he told me, and even more, why always the theoretical physicists are referring to coordinates? They are an unphysical human construction. You should write everything with differential forms. And he was completely right too. And for this reason, I want to show you how to apply these ideas to the ideas of gravitational waves, how to write them in terms of differential forms with a field line, with an spin connection, and how distortion has an effect on the propagation of different kinds of waves, like the electromagnetic waves or the gravitational waves or any kind of wave. And well, just following the advice of Zbigniew, I want to mention that the Greek indices will refer to a coordinate basis. I won't use them, just only for showing how in physics you typically write some expressions. But in general, all the ideas are written in terms of differential forms. Okay? And well, we have the typical four-dimensional manifold, and we define the spin connection there, and its covariant derivative also this way. And in terms of them, we can define a two-form curvature. It is there.
Sorry, Fernando. Hello.
Yes.
We see only first slide on your show. First slide. We don't.
Here's a slide. So you're not seeing the other slide?
No.
Oh,
no, so far only the first slide.
Oh, okay. Now, what are you seeing here?
The same.
Same slide. Yeah.
It looks like an editor.
Okay, I will share it again. Okay.
That's correct.
Okay, then now you are seeing the.
It says contents.
Okay, now it is working?
No,
yes, it is.
Yes, it is
Yes,
working.
it is. Okay, okay, wonderful, cool, thank you. Then, okay, here we were saying about the coordinate basis and about the orthonormal basis. I will use the Greek indices to refer to the typical physics expressions, but in general, all the calculations are done with the differential forms. Okay, and we will be using the typical spin connection, its covariant derivative, and to form a curvature and the torsion, which are defined like here. It is the typical expressions we get from the fiber bundle. So in terms of them, we can also define a contortion one form as the difference between the spin connection and a torsionless spin connection. And also the Riemann curvature to form, like it is shown here. Okay, so now we can start with waves, okay? And it happens that everybody thinks they know what the wave operator is, but it is a bit tricky, and you realize that when you ask what it is to physicists or mathematicians, a physicist will say it is the Beltrami operator, and in general it is defined like something like this equation here. But if you ask a mathematician, they will say it is the RAM operator, like this one here in terms of the exterior derivative and the co-derivative. And then, well, here is the co-derivative. So who got it right? Well, the answer is evident actually, and it is the mathematicians in this case. And it is because of the following. It happens that both operators are related through something called the Weisenberg Identity, which is something like this, okay? And why I put a mess there? Actually, it is because it is a mess. It is a result with a serious aesthetical problem. It happens that the general result is beautiful, and it is from the first half of the 20th century. But in general, it is so poorly written that in practice it is almost useless. And it happens that we know it is not due to Weizenbach. All the people call it the Weizenbach identity, but it is not from him. Actually, no one knows who first discovered that. My theory is that it was the RAM, actually, but the result is so ugly that the fatherhood of this result is unrecognized. So let us see some examples of this and how to solve that. When you have a circle on something, it means the torsionless version of something. Okay? For instance, you may have the Maxwell equations there, and then you can write it in terms of the coordinates you will say in physics, and you get something like that if you write it for the one form A. But if you write the same equations for F, it changes. These are with two indexes is the torsionless Ricci tensor, and the one with 4 indices is, of course, the torsionless Riemann tensor. And it is this expression even if the background has a non-vanishing torsion. It is some kind of strange. And even further, if you have other two forms, like the Riemann curvature to form, they are related through this, which is much more messy. And the only difference is that it also has some indexes in a Lorentz representation. So the relation between both operators is non-trivial, actually. So how we can understand this relation? Actually, you need a map. This map here, which map P forms in P minus Q forms. It is defined through the Hodge dual, then Q field binds, and then a new Hodge dual. Okay, And the interesting thing is that the case Q equals 1 satisfies the Leibniz rule. So it is kind of a differential operator. And what makes it interesting is that regardless of torsion, it is we have this identity here, that the code derivative can be written in this way in terms of the torsionless L covariant derivative. And if you use this, it is very easy to write all this mess in this form, this equation which relate both kind of operators. So this thing which was messy, when you make a good map, it gets really small and useful. And what we learn from here is that first, that the electromagnetic waves are insensitive to torsion. And actually, in this context, we see why. It is because in the left side, we have no information on the torsion of the spacetime. So we cannot have that information on the right-hand side neither. Now, what will happen about gravitational waves with a non-vanishing torsion? How they will behave in this context? Actually, that is kind of hard because if you make a perturbation of the field line, it is different. It has it change in a Lorentz representation, and it happens that obviously this operator here does not make sense. You should have something like with covariant derivatives there in order to make sense of this kind of expression there. And it happens actually that the code derivative has two different generalizations. The first one is kind of obvious, but it is actually ugly. And the second line is actually a much more useful one. Both of them are the same when the torsion vanishes or when you have some scalar P form. But for fields on a representation of the Lorentz group, then both expressions are different. And it just happens that this second line is important because it satisfies a generalized Weisenberg identity, which works beautifully. It is defined like I'm showing it now, and it works so well actually because these operators here, with this D, which is in the lower part, satisfies an open superalgebra, and all that makes everything very smooth. And it just happens that when you make the calculation with gravitational waves, they just pick up the Weisenberg alternative, this more beautiful generalization to construct the wave operator. And from that, we can conclude two things. First is that, as I say before, electromagnetic waves are unaffected by torsion. So we should never see any torsional lensing for light, for instance. But for gravitational waves, it will be different. It happens that torsion creates an anomalous propagation of polarization and amplitude. And this effect we should able to measure in some years in the future. The simplest scenario for this would be if dark matter would be made up for instance of fermionic particles. In this case, it will be a source of torsion. And if we have some kind of multi-messenger observation, something that creates both gravitational waves and electromagnetic waves, we should use that to see if in the space between us there is or not a non-vanishing torsion. And even if weak, this kind of effect should be detectable over a cosmological distance. Not with the instruments we have now, but with instruments which we will have in the next decade. So some conclusions here. Well, first, in the math side, that we have some Riemann generalizations of the co-derivative of the Laplace-Lichnerowicz, the RAM operator, of the Laplace Beltrami operator. The Weisenberg identity is intelligible now, and now it is actually useful. These ideas are easily generalizable to other superalgebras. And it works so nice because it actually creates an open superalgebra of differential operators. In the physics side, I can say now very briefly that gravitational waves are influenced by a non-vanishing torsion. It does not change the dispersion relation of gravitational waves. It does not change the speed of them, but it changes the polarization of the gravitational wave, and it will amplify or dampen the gravitational wave amplitude. And this effect will be should be observable with this experiment here with LISA. It will be a gravitational wave detector in the space. It will be there. It should be like in 2034. And with this kind of instrument, this kind of effect should be visible. So, well, thank you very much. Gracias, and dziękuję. Well, and thank you very much for the invitation.
Thank you.
Gracias. Oh. Eso de Yankuye es un buen gesto, ¿no? De recordar aquí Polonia. Tengo entendido que Valerie Boeglasov quiere hacer algún comentario. Perdón que interfiera, pero vi aquí su comentario por si no lo han visto. A ver si está Valerie.
Can the last speaker stop the screen sharing, please?
Yes. Yes. Stop share. Okay. Now it is okay. Yeah.
Yes, that's good. Thank you.
Okay. Yeah, thank
you. No sé, a ver. No, yo creo que no está activo, pero
ya,
bueno.
Hilda, Valerie, todavía no seguían espectadores, ya lo acabo de ascender.
Ajá, pero creo que no, tiene que aceptarlo y a lo mejor no, a lo mejor ya aceptó, ya.
Duvuglasov is an attendee.
Ya está, entonces a lo mejor ya puede. Doctor Valerie, ya está aquí como panelista para su comentario a Fernando.
Now it's good. He's panelist now.
Ya puede hablar, doctor Valerie.
In chat you put in chat I put my comment about physicists, and for physicists it's not important how to call some operator first. Next, moreover, it's not important which formalism used, differential forms or coordinate formalism or something else. For physicists, it's important, observable. All others things contribute to blah, blah, blah. Unfortunately, I didn't see that some observable is different in differential forms formalism or in coordinate formalism. Even in Algebraic relativity, groupoid relativity, in my opinion, observable will be the same. If calculating Algebraic groupoid relativity or in well-accustomed relativity for observable. Observable will be the same, sorry. I didn't see.
Yes, actually, what I think is that you are right in some way. I mean, the language is just the language, and geometry is the geometry independently of that language. But it happens that some languages are much more useful and much more transparent to get to some ideas. I mean, you could also try to answer this problem with the traditional language of tensors, but it will have been a nightmare actually, and you can see that precisely with this Weisenberg with the Weisenberg identity. There you see a result which was known for more than 100 years, but it was so messy that it was almost useless. But if you write it in a much more elegant language, it turns useful. So actually the language is not fundamental, but it really helps to choose a good language. Actually, I will say that is the point there.
Okay, thank you.
I guess this concludes the morning session. I mean,
no, we have, excuse me, we have one more presentation. Maybe you don't have the corrected schedule, but it is now when Professor Koshik.
Disconnection.
Excuse me? Okay. Professor Koshik.
Disconnected. I don't have audio. No audio.
Creo que Bill Page tiene algún problema. No sé. Ah, ok, ya.
We were disconnected, I think.
Pues si quieres, preséntalo, Jesús, al doctor Koshik.
Yes, but I don't know if the problem is with. Okay, I'm going here. Wait a moment because I have. You are presenting now? Mm-hmm.
I'm just trying to share my screen just to check whether it works, but it seems to be working.
Yes, el profesor Koshik prefiere que él compartir su pantalla.
Sí, está bien,
Entonces,
está bien, sí.
Hay que quitar la presentación que pusiste. Un momento nada más.
Él la tiene, no nos ha mandado a nosotros presentación.
Ok.
Sí, nosotros la tenemos.
Estaba, nada más un momento porque, perdón, aquí,
We still have 4 minutes, right?
Yes, I have not heard your dates for your presentation. Please, ¿tú tienes, Hilda, los datos del profesor para su presentación?
Pues los tiene en la pantalla, puedes comentarlo de la pantalla.
Bueno, simplemente, ok. Then, profesor, the next speaker is Professor Koshik, that is going to present that is going to present the algebraic loop of relativistic velocity refined and wide for space-time travels. Professor Jerzy Koshik from the Mathematical Department of Southern Illinois University. Welcome, Professor. Go ahead, please.
All right. I hope you can hear me.
Yes.
Okay, great. Sorry for the head. It is not lack of respect. It is just my headset stays better with the head. So thank you very much, Hilda and Ilda and Jesus for inviting me and for organizing this beautiful conference. And maybe I should start with Zbyszek. Zbyszek, or Zbigniew, was my friend for most of my life, and since 80s, unfortunately, a distance friend. We shared interest in many topics, and definitely in basic principles, and especially search of aesthetics and simplicity of the description. Is exactly what Fernando showed us. Is a good example, actually. And our conversations, on everybody's conversation with Zbyszek, are very often very stormy, as you know, let's say emotionally charged, but I miss them dearly. And it was part of the important ingredient of Zbyszek's charm. And let's see, relativity was one of the recurring topics. We never achieved full consensus on anything. And more funny, at certain point, Zbyszek forbade me to ever cite him or even thank him. Well, I disobey him today because I owe him a lot for rethinking basic stuff. And even if you don't agree, my narration of the topic changed thanks to him very much. So because I have pretty short time, I decided to choose this as a main topic. All right, so let me start here. Algebraic loop. Let me see if it works. Here. This is slide number 1 now, or number 2, and I hope you can see it. If not, please let me know. Loop is a in general quasi-group with an identity element. It means set with the binary product, with a unit element, and left and right division, but we don't assume any associativity. I learned about loop from, I think, first time from Larisa Zbigniewa, and maybe Ludmila Sabinina as well, in one of the conferences Zbyszek organized, and he insisted that physics should be done with more interesting structures than only groups. So loop is an example. And let me here right away introduce a Menhir loop. That's the name I have chosen, is not maybe perfect. What is it? Well, pick up any of the division algebras. So F here, stands for real numbers, complex numbers, quaternions, or octonions, and define the product. The product is like a Finite addition, a plus b at the top, and the bottom 1 plus conjugation of a, which is well defined for most of them except the real numbers, times b. So let's call it a Menhir group. Of course, division is not defined well because of the non-commutativity. So by this fraction, we understand that the bottom is on the left side. We just multiply by the inverse of the bottom. Next, exchange it a little. So here we have, just a reminder, this is our Menhir group. And we can study now that to what sort of non-associativity it sort of is subject. So one is pretty obvious, power associativity is satisfied. It is a special case of left alternate associativity when you have A, B, that's fine, but you cannot put B in front, so that's pretty weird. And then I studied a lot of other possibilities, and this is the only one which showed up as satisfied even by octonions, and it doesn't have a name, so I left it without a name. To study them, by the way, I use this sort of diagrams which allow me to, like, not to miss any of them. And I guess you can easily follow what it means. This is like a bracketing, but turned into like a tree. We don't have to go into this. If you want to use it here, if you have like an empty circle, this means these two elements are the same, like A. This is like, for instance, Mufang identities expressed geometrically, and this is this Menhir loop identity, which you have seen. Okay, so we have this box, let's call it the box addition, okay? And you can then think about box multiplication by 2. So obviously, how do you multiply by 2? You just add 2 elements. So A plus A, you can easily see it turns into something like this. And you can actually call it that this is 2 times A, except we have to introduce also a box multiplication. Well, you can have an inverse, like division by 2. So we have another one. It is just the inverse of this map. It's easy to calculate. So this is half by A is this. And if you compose it, you're getting, of course, identity. And so this is the notation we can use. A divided over 2, but this division is written with double line, so not to confuse it with just A over 2. We can also call it by maps. So this is mu, and this is mu, the inverse, let's see this way. And then let's define a new loop. The new loop is the same set, okay, but with a different addition. Namely, you take two elements, divide them by 2, means apply that mu, add them, and then multiply back by 2. So you can think about this as a deformation, okay? So the square is our original addition, and this is a new one. And we have 2 loops, this and the double loop. Yeah, I'm sure. Oh, and here is a simple exercise. If your field or your algebra, division algebra, is real numbers, then both of them actually coincide, which is a little magic, which later will show up. Nothing strange about this. This is something I'm sure many of you played in high school, how to change addition into something new. So like, for instance, this, or for instance, this one, you apply a function and the inverse function, right? So for instance, multiplication turns out to be a deformation of addition, of the regular addition. Okay, so why we are interested in this? I think I forgot to mention something. Namely, to have this division well defined, we have to stay within a disk of radius 1, okay, or less than 1. Okay. Why do we want to do? Well, I'm interested in this loop. So we're coming to the problem of relativistic composition of velocities. So you have somebody running over something else, which also is moving. what would an observer sitting outside see as the velocity of this person here, this James Bond, let's say, on a train. B is measured as a velocity with respect to the train, and train is going with velocity A with respect to ground. How do you deal with this, right? So the first answer was given by Poincaré a year before Einstein, and that's his famous equation. This is good only for collinear velocities. You can think about this as like one-dimensional space, and that's you can easily derive it. By the way, here velocities are in terms of natural unit, means speed of light is 1. And that's like interesting composition from the mathematical point of view. We have an abelian group, which is the segment between -1 and 1 with this addition. And here are some simple maybe examples. Half plus half will be 4/5. You never exceed 1. Even 1 plus x, 1 is forbidden, by the way, but if you try, you still get 1, okay? Now, the question is, okay, what if the speeds or the velocities are using the full 3-dimensionality of space, means they are in different directions? So Zbyszek made me aware that this equation doesn't even show up in Einstein's writing. And the first person who ever published the result is Christian Müller in 52. And I noticed that in a no current, and Zbyszek noticed, he just showed almost no current book on relativity showed this equation, because you don't want to scare young people away from physics. And it looks horrible. The aesthetics, aesthetically unpleasant, let's say this way. Can we do anything about this? Well, one thing is that this addition is non-associative. And I think it caused a big stir some time ago. And this is what also motivated Zbyszek to come back to this problem. He found non-associativity of the thing unacceptable, that something is profoundly wrong with our understanding of this. I'll try to simplify this equation into something much simpler. And here, I'm just recalling you, look, compare it to Poincaré. There's some core inside of this, but not really. If you replace here V and W by real numbers A and B, this eventually, after some cancellations, will become this. This is a good exercise, basic exercise. Okay, so here's the good news. Okay, suppose you have two velocities which are not aligned. They make a plane. In this plane, the two vectors express them as complex numbers, right? Because complex numbers is like, you can think about this as a plane, unguard, right, a plane. So this is what you have. You'd like to have to add those velocities in the way Mr. Müller, Christian Müller showed us. So this is what you do. Go with these velocities to the menhirs with this map mu. You have now two of them. Add them within this basic loop, the menhir group, and then invert the map, go back to complex numbers, and you get exactly the right answer, right? So here it says, so V plus W, the addition of velocities, would be go to the menhir description of velocities, add them in the loop, and do the inverse. By the way, this mu map, let me go back. Where is it? Here. You see the mu map, if you double it, notice that you're basically scaling A, and the inverse map is rescaling A. So you keep the same direction, you just make them shorter or longer. All right. So here's an expression once again. Start with the two vectors, expressed as complex numbers, go with mu, add them this way, and undo the map. Here's an example, trivial example. Say one velocity is 3/5, another velocity is here complex number, so they are definitely not aligned. You can easily check that this is half of this number, and this is half of this number, but half in terms of the loop. So simply add this in the loop way to see that this is the same thing. So these two numbers, just add them and undo it. So this means rescale it back to what it is, and this you can easily check it matches exactly with the calculations with the standard Miller equation. So this is like a miracle. And I want to show you, like, what does it mean geometrically? Okay, these are the two velocities. You find the Menhir's descriptions. They are rescaled, as you know, vectors. Then forget about the original vectors. There was a geometric interpretation of this product of the loop, which I'm showing you here. Make this line through 0 or origin and B, and make a circle going between these ends and A. Then do another line here through minus A, do another line, then they intersect. Well, this is the Menhir addition of these 2 points. And then you have to rescale it back to vector of velocity. So these 2 velocities, they add up not as a standard vectors, but they will be there. Okay. Now, I showed you this with complex numbers, but it goes with quaternions and octonions. In terms of complex real numbers, the thing is, as I told you before, both products are the same. And this is why the Poincaré addition looks like similar. And this is a cool part of it, that this Menhir addition is really similar from the formal point of view to Poincaré addition. I don't want to bother you with going through the exact thing, but we're changing the groups. And what is interesting, standard correspondence between the Lorentz groups is, special linear matrices 2 by 2 over complex numbers correspond to our regular space-time. For the baby space-time, 1 plus 2 dimensional, it is SL2R. In terms of quaternions, SO15 would correspond to special linear 2 by 2 matrices with quaternions and octonions. Octonions are not good to really describe Lorentz group. It turns out you can use them, except in any particular boost, you can do only through a string of the maps using those matrices. So you cannot find like one single matrix, but just a string of them, and you can recover it. Now, with this description here, which I showed you, the new correspondence is a little different. You're using unitary groups of the signature 1, 1. And again, I don't want to go to the details because I don't think you can pay attention for that stuff. The SU1, for instance, this means a square minus b square is 1 for any of these algebras. You can replace these algebras also by Clifford algebras. But of course, it looks cool when you use just plain division algebras because they are almost like numbers, right? There are possible generalizations, and this is just, okay, innocent speculations. What about, instead of multiplying by 2, you deform your loop even further, add like k of them. It's like multiplication by k, and you have to define also the inverse map. And then that would be the box k, okay, the addition. So from this, at the bottom, basic Menhir loop, you can create the whole chain of the higher and higher, let's say, powers of this Menhir group. The second power is our relativistic loop of addition of velocities. But what about the higher ones? Is it like relativity in other universes, or maybe like good to explore for fantasy books which explore other alternative realities, right? Okay. I still have a little time. Oh, yes. So maybe I will just only quickly go over what was a very often conversation with Zbyszek. Like, what was the actually problem with velocity? Well, if you have this is space-time. If you have an observer which is like changing his position in space-time there, so this is his or her life curve. This is a unit vector, let's see, 1 day or 1 second. And then the perpendicular to this in terms of the metric in space-time would be space. What is velocity of observer which is going like this direction? Well, this is the unit vector of the other observer, B, and you can call it chronon, maybe, or chronon. The velocity is this. You have to go here from 1, right, and project it down, and this is velocity as perceived by the A guy. Now, think about this. If you have two observers, one is red, this is time, and this is space of red. This is time of blue and space of 2. So by simple projections, I didn't draw those lines, but the red one moves to the right with respect to blue, and these are the velocities of in their corresponding spaces. So you cannot add them and say they are 0. Remember, Einstein in his one of the basic papers says he's using the fact that reciprocal velocity and plus velocity will be 0, and he's using it to derive something like this. It doesn't, in space-time, it doesn't make sense. So Minkowski would disagree with him. And as you know, Einstein didn't follow Minkowski at the beginning very carefully, much on the later. So yes, so this is the problem, right? We just conceptualize velocity in the wrong way. It is always like projection and does not represent the true situation. The true situations are these two vectors. And this was one of the bone I picked up with Zbyszek. Zbyszek claimed that you need a third observer to define velocity. Unfortunately, he's not right now here to defend his thing, but I try to convince him that no, just difference between these two vectors is already something which does not depend on coordinates, and it's very well defined. Okay, yeah, so this is a big diagram of the concepts which I created especially for Zbyszek towards the end of our conversation of this time, just trying to convince him what is where. One thing we definitely agreed, that Lorentz transformations is a secondary thing. People who think that if you want to see velocity, or let's say addition of velocities through good mathematics, you have to use Lorentz transformations, means application of the Lorentz group. It is wrong, because the group doesn't act on observer in a sense. Lorentz group is just symmetry of the metric of space-time. Okay, now if you want to do well, I'm not going to go through all that stuff, but maybe in some of my writing it will show up. But this is naive conceptualization of special relativity theory through this. The true core, the central entity, is the inner product, and everything actually follows from this. Okay, this man here I showed you, if you want to know how I came up with this, I didn't stare at the equations until I simplified them. I did something purely geometric, like behavior of the peak of the images of the stars in the celestial sphere, and did some first geometric discoveries, which later are turned into this algebra I showed you. Okay. Also from the celestial sphere, if you go another way, you get the famous spin group and Penrose's understanding of the whole problem. So misconceptions. Boost is not an action of the Lorentz group. This is only symmetry. I already told you this. There is no need for a third observer to define mutual velocities, I think. Velocity composition is weird because it is based on a poor description of the situation with those velocities, those projections. Anything, if you look only at the shadows, you can get lost. It's exactly like Plato's shadows, right? And through reality outside. I found here maybe some, analogy. Like in music, if you resign from the natural temperament, who is like perfect, right? For the sake of equal temperament, your notes are slightly off the true values, which would make a perfect harmony in your ear. But thanks to this kind of error, we can enjoy much richer music because Bach wouldn't exist. Anybody with B, Bach, Beethoven, Beatles wouldn't produce the music they do in terms of harmony, if not the temperament. So natural. Right. Okay. So this thing with those so what they presented here, right? The loops. This is like not a perfect description of what's going on. It is the projection, but the projection which allows you to explore like beautiful mathematics, which not necessarily is the really true representation of what's going on. Okay, so it's enjoyable because you can use loops in physics, and this is always a good thing. I have still a few minutes. So this was supposed to be the end. This is why menhir. This is a typical menhir. You can find it in England. This is this paleoastronomy, right? The people try to observe the sky through setting stones in different ways. That's just for fun only. In one-dimensional case, when addition is very simple, you can design a very simple way of geometric addition of two velocities. This is zero velocity of light, one direction and another, and you have two velocities. And I showed to some of you a long time ago what you do. Well, draw a circle. Here, make two lines, two arrows, let's say, through one of them and through another one, starting from the top and the bottom, south and north. Doesn't matter which one you do first. And then connect the endpoints. And guess what? This would be exactly the Poincaré formula for A plus B. So this is like a nice toy you can take with you when you travel through the universe. Okay. All right. So this is it. Thank you very much. And I think you're already hungry because we have.
Thank you very much, Professor Kosik. If there are some questions, please. Can you make this directly?
Michael Hitter tiene una pregunta, le voy a permitir que hable, si están de acuerdo.
Adelante, sí, sí.
A ver. A ver.
Mientras, profesor Santilli, you want to speak, please put on your microphone.
Michael Hitter, are you speak?
Wait a moment, Hilda, ahorita el profesor.
Yes, thank you.
Yes, I can you hear me?
Yes, Professor Santilli, go ahead. No, again, your microphone, please.
I am okay. I think. Can you hear me now?
Yes.
Okay.
Yes.
Very well. Thanks. No, I don't. Perhaps I will correspond with the authors, but I don't have a question. Thank you. With the speaker, the last speaker, yes.
Entonces, Michael Hitter.
Okay, thank you. Michael Hitter, please make your question.
No, I don't have a question, sorry. I have no questions.
There is a question in Q&A from Gregis Kozan.
I don't see the question. Questions, please, but I don't see a question.
The previous one is
dismissed, open. I don't see any question.
There are two open questions.
I'm sorry, but in my
okay, maybe we can read the question.
Yes, you like me to read? I can. It says, "Dear Tkk, please read all the questions first, but ask each one separately, 1, 2, and 3. Number 1, do you confirm that hat addition of velocities is addition of binary velocities? Number 2, do you agree that the hat addition of binary velocities is ternary, means dependent on the third chronoparameter t? Number 3, is chrono t orthogonal to v, first velocity, or to w, second velocity? Gregis Kochan.
Okay, so following Zbyszek's mode of operation, the answer is no to each of them. No, not really. So I already forgot the first question. The thing is that, yes, the orthogonality is in terms of the inner product in space-time. Yes, the velocity of the second person has to be orthogonal to the chronon of the observer. But no, you don't need a third, let's say, observer to do this operation. So this is what we always talked about with Zbyszek. So I don't see a reason here. Now, the thing is maybe to understand what this addition of velocity is coming from. Those velocities have to be understood this way. You're on a planetoid. I cannot draw it here, but you're on a planetoid, so imagine, and you decide, okay, here, let me draw on the ground a vector. I will make a boost with my planetoid in this direction by this vector. And after this, I will do another boost in another direction, and I will draw it on the ground. Now, once you do the boost in one direction, your planetoid has a different situation in space-time. So this second vector now is positioned differently in space-time. So when you follow it, it is not addition of velocities in the original, space-time situation, but we somehow make a mistake of drawing it on our planetoid on the ground. So this is why this velocity is behaving in a funny way. So I followed this maybe chain of calculations, doing a very standard, vector calculus or calculations, and I got exactly the same equation as Miller. So I think this is what he and other physicists did, although they don't specify it very well. And then you'd like to see a velocity as something independent on the observer, then you have to make very careful choice of what do you mean by what. So no third observer. And Grzegorz, if you want more detailed stuff, you can send me an email maybe.
Okay, thank you very much for your speech. Then, in view of the time, we are going to stop here. We have 30 minutes for the next section. Okay, then we make the break now. Thank you.
Thank you.
Aunque se van a proyectar actividades culturales, ¿no? Ahorita.